All right. Welcome to today's webinar with the topic 785 nanometer versus 1064 nanometer lasers, and why we at Surstech have chosen to use 785 nanometer wavelength for our laser in our spectrometers. So welcome everybody to this webinar where I will sort of tell our story. We at Surstech provide spectrometers primarily to be able to use in the field, meaning they should have a limited energy requirement. They should be handheld, they should be small, they should be lightweight, cheap, and durable. So a little more than a year ago, we launched our latest spectrometer called the ARC Mark II, where we improved most things of the device. We improved the optics, make the focus much sharper. We introduced significantly more advanced algorithms, although I should say that every quarter we update our firmware with new features in the algorithms. But with all these hardware improvements on the Mark II, we also updated our algorithms in a way that we could not do with the previous device. We replaced and upgraded the motherboard or main board, which is the brain of the device. The sensor, the detector, which I will talk more about later, also was upgraded to a much more sensitive detector, allowing for increased improvement. And of course, the new operating system runs much more in line with what we want to achieve with the more advanced algorithms. So there was a big upgrade on the device side. But we still kept our 785 nanometer laser. And I just want to briefly go through a little bit what we mean with 785 nanometer. So that is the wavelength that we use for the light source. And in Raman spectroscopy, you use only one wavelength. So laser is the perfect light source in this case. And there are, of course, spectrum. It's a spectra from or gradient from very long wavelengths to very short. And we are towards the end in the visible range, you could say, meaning our laser is invisible to most people, although you can see the spot where it ends up. So Raman spectroscopy utilizes the shift. When light hits a molecule, almost all light is reflected or scattered in the same wavelength, what we refer to as Rayleigh scattering. And Rayleigh scattering consists most of the scattered light. So almost all light comes back exactly the same wavelength. And that is not something we could use. That is something we have to filter and sort of remove as much as possible, because that's not interesting for what we're trying to achieve. What we're interested in is the radiation that comes back at a higher wavelength that has shifted. We call it a Raman shift or a Raman scattering. And that is the light we want to collect and analyze to see the fingerprint signature for a specific molecule. And mind you, it's a very small amount of that light, so it's a very inefficient process. So you require quite a lot of energy to do this. And so you have to be careful and take care of that, whatever little light you can do, and try to get as much out of it as possible. And I will come back to that later. That also comes into play with 785, because 785 nanometer provides more of this Raman scattering than 1064 nanometer does. So there's a lot of talk about 1064 nowadays. It's a newer laser that you're able to use 1064 nanometer lasers in handheld devices. That's a sort of new phenomenon. And so the argument for why you would want to have 1064 nanometer lasers is that you have less fluorescence. And fluorescence is an interfering signal that can sort of outshine the Raman signal in some cases. And the lower wavelength you have, basically to a certain point, you will get more fluorescence. So if we were to go below 785, we would get even more fluorescence. But we also get more Raman signal. And so with 1064, we get less fluorescence, but also less Raman signal. And not only that, it comes with a list of different drawbacks. So not only do you get less Raman signal, it's also unsafe because you need to use higher laser power. And it's completely and entirely invisible. Even the spot where you shine the laser is invisible. So it's usually associated with a much higher price. It has a larger size requirement, a weight requirement. It relies on a very specific type of sensor called an in-gas sensor, which requires cooling, which in turn even more increase the power requirement. And you cannot use surface enhanced Raman spectroscopy, which is something that we pride ourselves in doing very well. So you're not able to do that with a 1064 nanometer laser. But you do get less fluorescence, that is true. So, considering these different wavelengths, again, you could not choose any wavelength when you're designing your spectrometer, a Raman spectrometer, relying on a one wavelength laser source. So you have to choose something that exists or is already developed. So there are a few different wavelengths to choose from. So there are other wavelengths in between. For instance, 830 is one that is sort of in between 785, but there are also others at lower wavelengths. But we consider 785 to be a very good compromise between the amount of fluorescence and the amount of Raman scattering. And you can see this is an inherent sort of physical property in nature that it's inversely proportional to the wavelength to the power of 4. So you can actually calculate how much more Raman signal you will get using a 785 nanometer laser compared to a 1064. So you get 3.4 times more Raman signal using 785. And Raman signal is what we use to analyze the molecules. So that's definitely one big contributing factor why we have chosen to remain at 785 nanometer. Another thing is that you have to choose an in-gas sensor. If we're at the range where we belong in 785 nanometer, you can still use a silicon-based sensor. In this case, with the ARX Mark II, we have a CMOS sensor, and previously in the Mark I, we had a CCD sensor. And so the upgrade to the CMOS sensor we have now is incredible for finding Raman signal. And it's small, cheap, and it does not require cooling, which is a very important feature because cooling, as you might know, requires more energy than heating. So it's a very energy consuming thing, and that puts strain on the power requirements and size, and you have to build in a cooling system in your device. If you move up in wavelength, as I said, you have to use an in-gas detector, which is typically larger, more expensive, and it also requires cooling. So you have to cool the system, which ironically can sometimes heat up the actual spectrometer. If you consider a fridge, it's both heating and cooling. So behind a fridge, there's a heat source. And it could be the same thing for some of these spectrometers, that the actual spectrometer gets overheated when you cool the sensor, which can render it difficult to hold when it's a handheld device. And of course, it requires a lot of energy. Here's another representation where you can clearly see sort of the span and wavelength ranges for when you choose different detectors. So yeah, it's clear to see that you have to switch from a silicon-based to an InGaAs based sensor when you move up to the 1064 nanometer laser. And when it comes to safety, as I said, it's more hazardous to use this higher wavelength for several reasons. Of course, it's entirely invisible, the laser light, but it is typically operating at 495 milliwatts, which is a lot of energy. So to compensate for the lack of Raman signal, you have to increase the power. And there's a reason why most of these 1064 nanometers handheld Raman spectrometers use exactly 495 milliwatts, because 500 is the limit to move up to a higher class. So the limit is 500 milliwatt to become a class 4 device. And so these spectrometers operate right at the limit to class 4. And it uses a lot more power. And so you do run the risk of damaging the material you're measuring on. And we try to keep it as a non-destructive method for quantitative or qualitative analysis. And you can lose that feature using 1064, and you can also put the operator in danger. So that's a very strong argument why that is difficult to just move to 1064 nanometer. Right, so this is taken from a research paper published last year by Crocomb et al., where they compared different handheld Raman spectrometers on standardized samples. And as you can see, the lower wavelength lasers at 532 and 638, they typically have too much fluorescence. If we then focus on the topic of this webinar, comparing 785 to 1064, you could clearly see that you have significantly more Raman signal with 785, although you have fluorescence. So the slopes you see in the spectra to the left are contributed to, is due to fluorescence. But you still get enough Raman signal. On the 1064, on the other hand, for some samples, you have virtually no fluorescence. But there are cases, there are samples where you do get fluorescence. And in that case, there is very little in these spectrometers to mitigate that fluorescence. So to say that there are no fluorescence with 1064, it's not true. It's just more rare. But you do find cases where you have fluorescence. Right. But what do we do when we do have fluorescence, as in the case here to the left? Well, we're used to mitigate that, so that we have put a number of things in place to handle these situations. And one thing that we do is what I'm going to explain here. So top left corner, we have what we call a raw spectra. That's all the signals that the detector picks up. So in here you have the reflected laser light, the Rayleigh scattering that we filter away. And then you have the sloping Raman spectra here with on top of the fluorescence signal. So what we do with that signal, it undergoes a very clever sort of mathematical operation in the first algorithmic step, which can very cleverly find what is Raman signal and then remove everything else that is not of interest for this type of spectroscopy. And then producing the spectra to the up right corner, where there is a much more sort of clear Raman spectrum. And then we have basically removed the whole fluorescence problem. And then that spectra, the processed spectra, is then used for comparison to our reference library. And we can identify it. In this case, it's fentanyl. So with these several steps, there are more steps in the actual device, but the principle is correct that we first produce a spectra without fluorescence, and then we can use that for our analysis. As the name implies, SURSTech uses also surface-enhanced Raman spectroscopy. Our devices can be used as a regular device, just point and shoot and run a measurement. But you have the alternative to apply SURS. And with SURS, you can actually also suppress fluorescence, because the Raman signal is enhanced, but not the fluorescence. So then you shift the balance between the fluorescence and the Raman signal to a more advantageous situation. And to our knowledge, there are no source technique with 1064. So these source surfaces that we use are only available for 785. So that's another strong sort of argument why we remain and keep using the 785 nanometer laser. So coming back to our list of pros and cons for the different wavelengths. So yes, there is a pro with 1064 that is less fluorescence, but you have a whole long list with drawbacks that sort of can render it not as useful as the 785. And we would like to put the fluorescence within parentheses because it's not really a problem. So for the reasons I've just explained, fluorescence can be mitigated, it can be removed from analysis, and it can be handled in a number of different ways. So it's not really a problem as long as you have enough Raman signal. And you get more Raman signal with 785 nanometer lasers. So I would like to thank you for your attention, and I'm going to now open up a chat function to answer any questions that you might have. So I got a question about the graphs. So I will go back to the graphs and explain what I mean with fluorescence. So I will try to, let's see if I can have a laser pointer. Right, so I hope you see this laser pointer here. So the fluorescence in this case it's all the signal that's sort of non-sharp lines. You can see a little bit of Raman signal here and a little bit here comparing to the spectra below. But these wavy, big, flowy lines are contributed to fluorescence. And in this case, here it's the sloping sort of, sometimes we refer to it as ski slope. It sort of curves up towards a maximum that's sort of, yeah, somewhere at the lower wavelength. And then you see the tail end of that signal where you also see the Raman signal. And in this case, the fluorescence is, again, the same sloping sort of signal, but here afterwards, at a certain point, it's cut off and filtered away, because you have to put in what is called a notch filter that cuts light below a certain wavelength in order to not get too much of this Rayleigh scattering. So both Rayleigh scattering and fluorescence is filtered away. I mean, in the hardware, not by any kind of algorithm or any software feature, but it's physically filtered away. Although there is since there's so much Rayleigh scattering, there will always be some Rayleigh scattering from the laser coming through. So that's why you still see the laser light here, and the fluorescence is cut at a certain wavelength. That's why it ends abruptly here. I hope that was answer to the question. I'm happy to answer any more questions you might have. So if there are no more questions after this webinar, then I would like to thank you very much for your attention, and you're always welcome to come back with any questions later on if there should be any. So thank you very much, and I wish you a nice day. Bye.